So today we're going to look at diode rectifiers. This is an essential component of power electronics in the sense that we're going to use them in a variety of scenarios to prevent, for example, currents flowing from an inductive load back into our system, to convert AC to DC, and in many other applications. In the last lecture, we looked at transformers. In a transformer, we are converting an AC signal into another AC signal with a different magnitude in the same shape. The idea here is to use a specific combination of diodes to convert a AC signal into a DC signal, or something that resembles a DC signal as best as we can do. And this is what we call a rectifier. In the next lecture, we're going to see how we go from DC to a different level of DC. And in the lecture after that, we're going to go the other way. We'll have a DC signal, we are going to go back to AC. Many components in radio frequency communications, or even your smartphone, will use some sort of diode rectifier, or simply diodes everywhere. And these are essential in mechatronics projects, as you're going to see in the slides that come. So in this lecture, we're going to review the principles of diodes, analyze and design diode rectifier circuits, and determine the effects of load inductance on load current. Okay, so this is not very complicated. Most of it will be a review from physics, but we're going to tailor that around our needs for power electronics. As I said, there are many applications of diodes and diode rectifiers. The idea of a rectifier is to convert the AC signal into a DC signal, or in other words, is to prevent current from flowing in one specific direction. This process is known as ratification. If we think simply about a phone, how we would charge a phone, we take a AC power from the outlet and you connect a transformer to your phone, but that component, that voltage that is applied to the phone to charge a battery is a DC battery. So it can charge electrons in only one direction. Otherwise, they would flow back and forth and the battery would never charge. So we need somehow to rectify the current and make sure that the current flows in the battery in only one direction. And to do that, you can use a rectifier. Another application of diodes is something that you probably noticed when you used DC motors before. A DC motor is an inductive load, essentially. It behaves like a large inductor. In this example here, let's assume we have this circuit, we close the switch, we load the battery, we load the inductor with a certain voltage and a current, and then we open the switch. When we open the switch, there will be a drastic change in the current. Di dt will change drastically, which means that the voltage across the inductor will also change drastically to prevent this change, or to try to prevent this change in current, which results in a large voltage. And when you open the switch, we'll probably notice sparks. And these sparks are coming from the inductor now trying to release that stored energy somewhere. Right? And this is a problem when you have, let's say, a high power system connected to a low power system, such as a microcontroller. We don't want any of that energy to be flowing into the microcontroller and destroying the low power side. So we need to use a diode somewhere here to prevent this energy from flowing back into the system. So to do that, let's do a quick review, very quick and rough review of how diodes work. A diode is essentially a semiconductor with two terminals, and it allows the current to flow in only one direction. We can make an analogy here with this hydraulic valve, where instead of a electrical current, we would have a flux, or a flow Q. And instead of voltage, we have a pressure drop. And in this mechanism here, if you apply a flow on this side, the flow can go through the valve. But if you go from the other side, this valve will block the flow from going in that direction. So again, the analogy here is that flow is the current, and P, this pressure drop that you would see across the valve, is our voltage drop. So the diode behaves in the exact same way. It will prevent current from flowing in one direction. The very first diode that was designed was for a telegraph, and it used those big vacuum tubes that you can see in your slides. It is not showing on mine here. But today you use semiconductors, so solid state diodes. The way to create them is relatively simple. We have what we call a N-type and a P-type diode, or side of the diode. On the N-type, we're going to add additional electrons and have free electrons in that side, creating a negative charge. On the other side, on the P-type, we are going to add some impurities to that material that would otherwise be neutrally charged to create now holes, to remove some electrons from that neutral charge, which will create a positive loaded side. These diodes typically use silicon as the main material, and another material that is added to create these holes or to inject additional electrons in the material itself. And here we form the N-type and the P-type. So the N-type has free electrons, and the P-type has additional holes in there. And once that is done, you're now going to connect them together, which means that when you put them together, now we have this charge that is not balanced anymore, is not neutral. And these electrons on the N-type will migrate to the P side and occupy those holes. As we do that, we know that an electron has a negative charge, which means that now the side here of the P-type will be negatively charged, and this edge here of the N-type will be positively charged. This creates now a voltage drop that we call here a barrier potential, P, or let's call that a V, that establishes there and prevents further migration of electrons from one side to another. And this is typically around, for silicon, 0.7 volts. Now that we've created this barrier will prevent, as I said, further migration of electrodes from one side to another, but will also prevent current flowing in one specific direction if we now use an external power supply connected to this. So let's see the first example here. Now we have a power supply, a DC power supply that we're going to connect that way. The positive side is connected to the P side, the negative side is connected to the N side. Now we see there that we created a very similar circuit when you have like a closed or any loop. When the current is flowing in one direction, we see that we have positive, negative, voltage drops. Right? It flows well as in a regular circuit, which means that if here we have a barrier potential of 0.7 volts, from 0 to 0.7 volts, current will not flow because you don't have enough potential to overcome that barrier. If the voltage here is then greater than the barrier, 0.7 volts, now current flows through the diode to the left. We call this a forward biased diode. It allows current to flow in one direction. Now let's reverse the battery. If you reverse the battery, that's the second case there. The negative is connected to the negative, positive is connected to the positive side. They will just push the electrons aside, but a no flow will be established. So the current flowing here is 0, regardless in an ideal diode of the magnitude of that voltage. Nothing new here, right? I believe you already covered this in physics before. This is a rough explanation of how the diode works. For our projects, we are going to represent a diode using this symbol here. This symbol indicates that the current is allowed to flow in that direction. And when you buy a component, you see a white side here. This white side indicates in which direction the current flows as well. In an ideal diode, we are going to assume that a voltage barrier that we have to overcome is 0. So long as the voltage is, let's say, is positive, current may flow through the diode. The barrier in a ideal diode is 0. We're also assuming that in the reverse direction, there is no current flowing into the diode if we now switch the sides of the battery. If you put that in a reversed bias configuration, no current flows through. So the ideal diode would be represented like this. If the current is negative, if the voltage is negative across the diode terminals, then no current flows through it. If the voltage is positive, then the current is allowed to flow through that. That's the ideal diode, and that's what you're going to use as our model. But in a practical diode, things are quite different. First, we need to indeed overcome that voltage barrier of 0.7 volts. And even you notice here, if we are under that 0.7 volts, there is a small current flowing in the diode, in the order of microamps. Another consideration with practical diodes is that if we reverse the voltage, we have a reversed biased diode, but that voltage is significant, is very high, there is a breakdown region here where actually the current will indeed flow. The pressure, if you think back on that analogy we did with the valve, the pressure would be so high that the valve would break down and allow flow in the direction of pressure, even if it's reversed biased. And that will remain there for a while, but once the voltage is removed after a certain time, the diode goes back to its original working principle. Right? But for the purpose of our class, we are going to assume that we are dealing with ideal diodes, even though when you use this in a mechatronics project, you have to account for that 0.7 volts drop in the diode. Very well. Now let's use a diode in this configuration here. A very simple ratification of the input current. We have a voltage, a sinusoidal voltage that are given to this voltage source. We have a diode, so the diode is conducting current in that direction so long as the voltage is positive, like that. So if you have a positive, negative voltage, current can go through. And let's see what happens at the voltage across the resistor, VR. If we input this specific waveform in the voltage, what happens in the output? The diode only conducts in the positive cycle of the input voltage, and current then flows through the resistor. In the negative cycle, let's say this cycle here of the input voltage, the diode is reversed biased and does not conduct any current, thus VR is 0. So our output that I'm going to plot here would look like this. All negative cycles are 0. Okay. If we reverse the diode orientation, then all negative cycles would show up in the output and the positive cycles would be 0. The average output voltage on the signal is easy to calculate, as any average voltage is 1 over t. T is the period. In this case, would be 2 pi. Integral of VDT over that same period. That's the average voltage that one would see at the output. Now let me give you an example of what we can do with this, with a diode. Let's consider this LC circuit. Is a LC circuit, and at the input we have a DC voltage. We have a DC voltage. Let's see what happens here. Let's assume to start that the diode is not there. We only have a LC circuit, and we have a DC voltage. Now, from control systems, we model this thing. And if we don't have any resistors, what should we expect to see as the current flowing through this? Should we expect that to reach a steady state? Should it be a sinusoidal? Should it be zero? What would you expect to see as in terms of current flowing through this when the switch is closed and if there is no diode? Any ideas? What is the waveform of the current flowing through this circuit? Does anybody have any guesses?
Someone said zero current.
Zero current, okay. Anybody else? Well, let's put it this way. This is, if you close the circuit, now if the diode is not there, we have two elements. There is no element dissipating energy. Right? So the current cannot go to zero because there is nothing dissipating energy. The confusion may come from the fact that here we have a capacitor and here we have a DC voltage. Right? But because you don't have anything dissipating energy, when you close the switch, now the voltage goes to the inductor. The inductor loads itself, it stores current there, and then discharges that to the capacitor. Then the capacitor takes all the input voltage, and once it's fully loaded, it goes back to the inductor. And this process repeats indefinitely. If we had a resistor in the way, then in this process of transferring energy from one element to the other, energy would be dissipated and eventually current would settle to zero. But here that element is missing. So this cycle will continue forever. The actual shape of the current would be a sinusoidal waveform, even though the input is a DC input. Let's see that in the equations. Easy to see. If you apply Kirchhoff's law here, or Kirchhoff's law, one of those, we can write this expression that we saw in control systems. Vs equals to the voltage across the inductor plus voltage across the capacitor plus the initial voltage across the capacitor. And let's assume that this is now zero. We can take the Laplace transform of that expression and solve for I of s. And we see here that this gives a second order transfer function. And this is clearly the Laplace transform of something that resembles a sine waveform. Omega here is 1 over LC. This is a simple modeling from control systems, so I'm going to skip all the steps. And when you now do the inverse Laplace of equation 3, we get here. Vs is the input voltage. Omega n is the natural frequency of our system here, which is 1 over square root of LC. And the current now becomes a sinusoidal waveform. So if we didn't have the diode, this current would be positive and negative. But not, even though the input is a DC. Now, let's add the diode. What happens now? The current that would otherwise fluctuate can only go in one direction. So this system does not allow current to flow in the negative direction. Look at the diode again. Current can only go that way. So only one cycle will be allowed. And as soon as the current now tries to reverse, then the system reaches a steady state. The initial current is zero with the diode. Without the diode, the current always fluctuates. So the current is given here, I of t equals to that. We can find the voltage across the capacitor by simply integrating that. So 1 over c integral of I dt is the voltage across the capacitor. And when you do that integral, this is what we see. This is the result. Okay, this is the result. We see that when we start at 0, time equals to 0, this goes to 0. And when we reach, when omega times t, omega n t is equal to pi, this gives cosine of pi and everything tends to -1. And this will be achieved when t equals to pi times the square root of LC. When you have that and you replace time in t, we have cosine of pi. Cosine of pi is -1. So this whole thing here becomes 2. And the final capacitor voltage now tends to 2 VC, 2 times the input voltage, and the system reaches a steady state there and is blocked there. So this is an interesting arrangement to now double the voltage from the power source. As soon as it's turned on, it will take a few microseconds or milliseconds for the capacitor to load, to charge to 2 times the input voltage. And you can now have another one of these elements, let's say something like this, in cascade. And now we are going to go up to 4 times the original input voltage and so on. This circuit is typically used in superconductors to create high voltages from one single power source. But you see now the addition of the diode messed up the whole system. Nothing is linear anymore, and everything is a bit more complicated to analyze. Are there any questions so far? No? Okay. I posted a Simscape code that shows how this works in the lecture module. Download it and try to run it. You have 2 benefits of it. First one is you see exactly what is happening here, and the second one is first model of Simscape that you can later use in your design projects. It's in Simulink, basically. You should all have Simscape installed in your computer. If that is not the case, then please contact IT. They will add that module to your Simulink, to your MATLAB account. Okay, so that's one application of diode as far as power electronics is concerned for us as mechatronics engineers. Now let's see another application. These are the freewheeling diodes. The idea is to prevent charges from inductive loads from flowing into the system. This is the arrangement we have. Let's assume, for example, that this load here represents, let's say, a DC motor. If we had a power source there, a DC power source, that would be exactly how a DC motor would be modeled from the back EMF. And here we have 2 diodes. So this diode conducts that way, this diode conducts only upwards. Now only conducts when voltage is like that, and this only conducts when voltage is like this. So here we have 2 operating modes. The first one is when the diode is closed. We have a DC input, and you have a diode, or the top diode and the middle diode. When the switch is closed, which one of these diodes conduct? Well, if you close the switch, we have a positive side of the battery up, so this will be positive, negative. This diode conducts. The other diode will be positive, negative as well, but it only conducts in the opposite direction. It would be reversed, so this would not conduct any current. So the equivalent circuit would be represented as that. And if we now neglect the voltage drop across the diode, we can write that V is equal to I times Ls plus R, which means that the current is 1 over Ls plus R times the voltage input. The voltage input, when you close the switch, is a step. The Laplace transform of a step is 1 over S. And now we can take the inverse Laplace transform of this, and this should give Vs. Sorry, let's make it a bit more generic. Let's assume that the magnitude of the input is Vs. So this gives Vs over R divided by times 1 minus exponential of negative R over LT, something like this. If we give sufficient time for this system to establish the current, then the steady state current is Vs over R. We close the switch, the steady state current will tend to Vs over R, and this is now the initial condition in the inductor. Now the inductor is now loaded with that steady state current. Now let's open the switch. As we open the switch, the power source is now disconnected from the supply. Sorry, the power source is disconnected from the circuit, and we are only left with this part here. Because the current is now stopped to flow, the inductor will reverse its polarity and will now be charged this way, right? Because it is preventing any further changes in the current. It needs to apply that additional force there. Now the middle diode is forward biased and will conduct. Remember that this inductor is charged with the initial current I0, which is Vs over R from the previous step. We can now do Kirchhoff's law to this remaining circuit. It's very simple. We only have an inductor and the diode. So here we have the equation for it. The voltage across the inductor plus the voltage across the resistor is equal to 0. When you take the Laplace transform of this, we are left with L I of S minus L I0 plus R I of S. And you can now solve for I of S. I of S should be something like L divided by LS plus R times I0, something like that, I believe. And when you take the inverse Laplace transform, here is now the new current through the circuit that simply decays and loops around here until it dies out to 0. Yep. Did you have a question there?
Isn't there an S missing in the LIS in the first term?
Yes, there is an S missing, exactly. Yeah, there's an S here. Thank you. Now let's see the current that flows through the load. The current that flows through the load initially goes up, establishes at I1, which is Vs over R. When you now open the switch, the current continues to flow, but it now flows in the second loop here, and now eventually dies off to 0. What is the current through the diode? Let's plot the current through the diode here in this graph. How would that look like? If the switch was open at time t1, then up to time t1, there is no current flowing through the diode. At time t1, we now jump to the initial condition from the inductor, and then eventually it dies off to 0. So this would be I2. Okay, and this is a freewheeling diode because now we provided an additional path for the energy stored in the inductor to be dissipated and is not going to flow back into the power source. If you do any mechatronics project with inductive loads, you must make room for a freewheeling diode and prevent, even if you power on, take like a DC motor and take a wire and just connect it and remove it by hand, you see that there are sparks there. And these sparks are coming from the inductive load. So if you have a freewheeling diode, that should not happen. Any questions here? No? All right, I'm going to skip this one. Let's do one exercise. So here we have current flowing through a diode is given like this. And the current waveform, okay, we have the current waveform of a diode shown in the figure. Determine the average, the peak current of the diode. Assume a half sine wave. Very well. So this is what we see in the diode. We are assuming that this comes from a sine wave, and this is the rectified voltage from a diode. Our question is, what is the average voltage, the average current through the diode? We see that the peak current is given here is 500 amps, but what is the average? This is supposed to come from a sinusoidal waveform, And clearly, this was rectified. So we should have another cycle here that is not showing. And we should also have another cycle there that is not showing, but they were rectified and became 0. We see also the magnitude here is 500. So if this is indeed a sinusoidal waveform, we can say that this should take the shape of ID equals to negative 500 times sine of omega t. Why negative 500? Because clearly the sinusoidal waveform here is shifted. A sinusoidal waveform would start at 0 and go up, but it's actually negative, hence the negative 500 here. Omega is the frequency in radians per second that we can take from the graph here. What is the period of this signal? The period of this signal is from 0 to 200. It will start to repeat. So the period is 200 microseconds times 10 to the power of negative 6 seconds. The frequency in hertz is 1 over t, and this is 5,000 hertz. Omega in radians, the frequency in radians per second is 2 pi times f. Okay. Good. So now that we have this information, we know the period, we know the shape. Is it clear that ID follows this equation? Any question? You see where this is coming from? Right? It's a sinusoidal waveform, but it's negative in the beginning, hence the negative sign. 500 is the magnitude given here.
Question.
Yep.
I see that the period, you got it from the very start of the plot to the 200.
Yep.
Between 200 and 500 is 300. So maybe I'm not understanding something. Is the wave delayed or something between those 2 points?
Yes, there's this same dead zone here applies, right? So you are saying that this should have been 300?
Yeah, the dead zones are different lengths, so it's kind of confusing me.
Right, let's put this to avoid that confusion. Let's assume that this is 300.
Okay.
I think that's fair. Yeah, that's fair. It's a good point. That's 300, so we have a cyclic motion there. Okay, so now we can do the average current through the diode. So the average current now is the integral of 1 over t, integral of the diode current through one period. But we can now split our period into 2 different parts, one from 0 to 100, where the magnitude is 0. Right, this goes from 0 to 100 microseconds, and plus 1 over t, integral from 100 to 200 microseconds of negative 500 sine of omega t dt. So this first part here is 0. The second part becomes 1 over t omega. Actually 500, let's put a 500 here, over t omega cosine of omega t from 100 microseconds to 200 microseconds. Right, when you take the integral of this, that becomes cosine over omega, hence omega here, right? And this 500 is the 500 there, and it becomes negative cosine, so the negative sign disappears. Okay, now we can continue to expand this. 500 divided by that, omega is 2 pi f cosine of 2 pi times f, which is 5,000 times t from 100 microseconds to 200 microseconds. T is equal to 1 over F. So this is 1. All right, and all we need to do now is to replace 200 minus the same for 200 minus the same for 100. I'll give you the answer here. This is going to be 159 amps. 159 amps. Okay, that's the average current through the diode. This is interesting because this is exactly 2 over pi times ID. If we had a full wave rectification, so if this part here was also positive, this is what we would have, 2 over pi times the magnitude of the input, but because you only have half wave, then this is 1 over 2. So this constant will show up every time we have to calculate the average, right? But because this is half of a waveform, then we have the 1 over 2 here. So ID 500 times 2 over pi times that should give the same results. Any questions?
Yes, Professor. I'm still having a little bit of trouble understanding why you have the 1 over t term in front of the integrals.
Yep. So this is the definition of. Let me go back here. This is the definition to calculate any average. It's always 1 over t because you need to account for the period you are taking that integral. All right. If you only take integral, let's put it this way. If you only take integral of the sinusoidal waveform, then what you are doing is you're calculating this area here. Right? The area would be the integral of this curve. This is not the average, it's just the area. Now we need to distribute that area over the entire period of the function to find the average, because your sinusoidal waveform is not only happening here, it's happening here. It's repeating after this amount of time. Right? Hence the 1 over t. You want to take this area and distribute this area over this period. Hence 1 over t. Any other questions? No? All right.
I have a question.
Yep.
Yeah. So generally speaking, are you saying that well, technically the final answer should be ID over pi, right? With your final
Yes.
answer?
Yeah.
Okay. So then and you're saying that when you are when you're using full wave when you're looking at full wave rectification, you'll have 2 over pi times ID as your final answer.
Correct. Yeah.
Okay.
Yeah. So this is a constant. You've probably seen this constant showing up before. This is 0.6366. Does this ring a bell from electrical circuits? No?
Not really.
Not really? Okay. Well, anyways, would be this times the input would give you the average for a full wave form, and half of that 0.31 something would be the half waveform.
Question.
Yep.
Maybe I feel like I'm missing something. How come the average for a full wave isn't 0? Because if you take the integral of a sine wave for one period.
Very good question. Very good question. The average for a waveform would indeed be 0 for a non-rectified waveform. But what I meant by having a full waveform would be a rectified waveform. So it would be like this. Everything is rectified.
Okay.
Right? So this is non-zero. Indeed,
Okay.
the average of a sinusoidal waveform is 0. And that's why, exactly why we use RMS instead. The root mean square voltage.
Okay.
When you do this calculation here, we are going to take the integral of this, and you're going to also take the square root of that. So now, even if you have a sinusoidal waveform, non-rectified, it's going to be non-zero. And the RMS is now an indication of how much voltage you would need in DC to create the same amount of heat as in AC. Right? And that's why we have the notion of RMS. root mean squared voltage. Because indeed, if you take the average of a sinusoidal waveform, it's 0, right? But it is still delivering power. It happens to be in both sides. So hence the square that will make everything positive, and then to get rid of the square root. All right, so let's move on. Yeah, let me erase this first so my face is not in the way. And this is the fun part of a light board. Now let's look at how we can rectify a waveform fully, not only halfway as we saw here, because we are basically wasting half of the power. We are throwing away half of the cycle, and that's significant. So now let's make a specific configuration of diodes to allow us to actually use the full waveform. And this is the diode rectifier idea. In a diode rectifier, the objective is to have the output as a purely DC signal, as close as a DC as we can. So if we look here at the figure on the left, on the right, we see that we have an input that's an AC, and the output ideally would be that a constant line. That is a DC voltage or current, but that's not exactly what happens in practice. In practice, we have that a curly waveform, the output with ripple and some harmonics that will originate from this nonlinear behavior of the rectifier. Our job is to design a rectifier that will provide something in the output that is as close as possible to a DC, but it will never, depending on what you're using, be an actual DC waveform. Okay, I'm almost done cleaning this. There we go. All right. So now our process in this rectifier is to take this AC input, convert that into a DC, as close as possible to a DC. Now, in order to compare them, we need to compare the input and the output voltage that we generated. The input AC power, this should be input, is the voltage in RMS times the current in RMS. The output now is supposed to be a DC, so we'll take the DC component and multiply that. And then now when you divide the output with the input, this should be a ratification ratio of exactly 1. Exactly 1. But this will never be 1 because the output is never exactly a DC. You will see that here it oscillates, and we need to take only the main component of that waveform and then calculate the output using the DC component only, this shift of that waveform. And the rectification ratio ideally should always be 1, but it's actually not necessarily 1.
Question?
Yeah.
Can you repeat about the rectification ratio? You say it should be 1, but it's not?
It is not going to be 1 because the output that you're going to see is not a perfect DC waveform like that. It will be some sort of waved waveform from which we are taking only the DC component, multiplying that with the current to find the power output. That's one problem. The second problem is that the current and the voltage will not be in phase, but they should. They should always be in phase, but the output current and the output voltage will be shifted, which means that the power factor now decreases. So the output power decreases slightly. So this rectification ratio will never exactly be 1.
Okay, thank you.
Yeah. So let's look at a simple full wave rectifier here. This is a center trapped transformer. So the idea is that you have a transformer, and you're going to take the halfway in that transformer, we're going to place one of the outputs, and on the other end here we have the other wire, which goes through a diode. Let's assume that we still have a ratio here of 1 to 1. In the positive cycle of the input voltage, we have positive, positive. So this is positive, positive, and the second branch is positive, negative, like that. R is our load. Which diode now conducts current? The top or the bottom diode? D1 or D2? In the positive cycle, we see that the top diode is forward biased, so current flows through the load through diode D1. If we now reverse the voltage, in the negative cycle, now we have negative, positive, so negative, positive, negative, positive. We see now D2 is forward based, and D2 now conducts current only. Interestingly, the current through the load is always in the same direction. It's always going towards the transformer. Which means that if you take now the waveform at the input that we have here, and you look at the voltage V0, which is across the load, we have a fully rectified waveform. All negative cycles now become positive. Negative cycles go through the second diode, diode 2, positive cycle are originating from the top diode. So all these parts here are going through diode D2, and the remaining is through diode D1. The average load voltage is the same. We can calculate as we calculated before, 1 over T, integral of 0 to T times the sinusoidal waveform itself, the rectified one. So notice the little maneuver that we are doing here, because if you only take the integral of 0 to T, it will still be 0, because in sine of omega T, we have no considerations for ratification. It's just a sinusoidal waveform, essentially. So to overcome that, we're going to take half cycle, calculate the average for a half cycle, multiply that by 2. All right, so here we have half cycle and a half cycle. All right, you multiply that by 2. And this now gives, if you solve this equation simply, will give 2 over pi times the input voltage, which is 0.6366 for a full waveform, fully rectified waveform. So 2 over pi times the input voltage. That's the average voltage across the load. Okay, 0.6366 Vs in the input. Right, and Vs, by Vs, I mean the peak voltage in the transformer input, not the RMS. Another interesting measure here would be to take the root mean square instead of the average. So same process, but now we are going to square the waveform and take the square root of that. What is the difference? The difference is that if you take, as was asked before, the average of this waveform, that is 0. If you take the root mean square, that is non-zero. So that will be the square of the waveform itself. So now everything becomes positive. We take the average, we take the square root of that, and that's the root mean square. The RMS is a quantity that alludes to how much voltage we would need in DC to create the same heat or the same joule losses as in DC. So let's say 100 RMS volts in DC, in AC, is equivalent to 100 volts in DC. If you take both and apply to a resistive load, they would dissipate the same amount of energy. Okay. So here we have, for a full waveform, a RMS voltage of 0.707 times the peak input voltage. And if you have half of a waveform, then it would be that divided by 2, of course. Now let's look at another arrangement here. This is another arrangement, is a full bridge rectifier. So instead of a transformer, we are going to use 4 diodes instead. in this configuration. So V0 is our load. Let's say we can put a resistor here. I can put a resistor there. That's our load. And this is the arrangement. So let's start with the positive cycle. When the positive cycle is acting, which diodes can conduct? This diode is forward biased, and so current can flow there. This diode is reverse biased, current cannot flow. This diode is reverse biased, current cannot flow, and this one is forward biased, so current would flow like that. So in the positive cycle, we have the current entering the system here, going through the load like that, exiting here, and going back to the source like that. All right, and the current goes that way. In the negative cycle, now we have negative and positive. This diode now can conduct. Sorry, this is the other way. The bottom diode can conduct. This one will go through as well, but it can conduct in the other direction. This diode right here can conduct, so current can go through it. It will enter the load this way. It will go through this diode. So here's the mistake I made, and back to the source. And notice again that the current is going, even in the second cycle, is going through the resistor, through the load in the same direction. All right, so positive cycle, we go like that. Negative cycle, current goes through here and back, and always through the load in the same direction. So this is what I call a full bridge rectifier. It doesn't use a transformer. It uses 4 diodes instead. Any questions with this? You have seen this one before, right? Have you seen this this thing before? Yeah.
Yes.
Yeah.
Yeah. Okay. Yeah. Go ahead if you had a question.
Sir, I just had like a question about the application. So I'm curious, would you, if you were to use a multimeter, would you be able to get a voltage reading on the resistor?
It depends on what the voltmeter is set to register. You would likely look at the RMS voltage. But the instantaneous voltage would look like that.
Okay.
The bottom one. If you put it, not a no multimeter, let's say a oscilloscope. If you put an oscilloscope, that's what you read, is the bottom voltage. A multimeter is likely to be giving you an indication of the RMS, depending on how it is set up.
Okay, got it. Thank you.
Yeah. All right, so now let's consider the same rectifier, and let's connect that to a DC motor. Here we have a lovely DC motor, RLE. You know what these stand for. And let's see what happens. So this analysis is fairly complicated. I'm going to skip the derivations because it took me about 2 days to figure out what was going on, because the textbook was wrong. It had a mistake somewhere. And I had to derive everything myself. It's fairly complicated. So I'm going to skip this, but I still wanted to show you what is happening in the current, because ideally the output current and the input and the output voltage should be in phase. All right, so the power factor is not affected. The input voltage and the input current should also be in phase, so the power factor from the input also doesn't change. We are working with highest efficiency. So let's see what happens here. If you connect this voltage through a rectifier to a motor, we have an input that is now rectified, that is given to the motor. We can do all the equations, we can model everything there. I'm going to skip all this derivation because it gets fairly complicated. But at the end, what I want to show you is the current. Look at the current through the load. That is what is happening. The current through the load is like that. Ideally, it would just be I0, would be a constant, but it's not. It's waved like that, right? So, well, that doesn't really seem like a problem here. If I have the equations here for you, so you can plot them in MATLAB and see which components would smoothen out the current probably the inductor would remove that ripple and make the current more constant. If you change the input voltage, it will shift up or down. So the equation is given there. You can play around with it. But let's look at the waveform. So this is the waveform of the current through the load. And let's assume that up to pi, we are working with a positive cycle. After pi, it's the negative cycle of the input voltage. How would the current look at the source? If this is the current through the load, how would the current look from the source? Is it the same? Is it the same current that is coming from the source? Yeah, any guesses? Would it match the waveform of the input, the current from the source? This is through the load after the rectifier. It would not, because from 0 to pi, we have a positive cycle. Our current is positive. So up to pi, it will match the input current. What comes from the source goes to the load. The source is going positive, the load is going positive, very well. But now in the second half cycle, after pi, the load, the power source is now in its negative cycle, so it cannot provide any positive current. It needs to provide a negative current, which will be rectified before it gets here, which leads to this beautiful curve here. This is the power, this is the current from the source. This is Vs, or let's call this Is. And this is I0. You see the mess we created by adding a rectifier. If we now take Is, we rectify that, we make positive parts become, negative parts become positive, that's what we get. And that's the load through, the current through the load. But you see how messy it becomes now in the power source. Things that were relatively linear now become completely non-linear, and you see this drastic change in the current direction coming from the source, because when you switch from positive cycle to negative cycle, the current from the source becomes negative. It will be rectified before it is applied to the load. So again, if we take the second half here, we multiply that by -1, that's what you have. Right? You see how complicated this can become. Right? And this is the current now flowing from the source. The top one is the current through the load. Okay, so this is for reference. It give you an idea that even though we are looking at something that resembles a DC, it's not really DC. It's a rough approximation of a DC signal. Later we can filter this out, but a look at the poor power source, what it has to do to deliver the required current to the load. And all the derivation is given here. You can go through it later. It's fairly complicated. I don't expect you to understand everything here. It's just for reference. So this is the main message for that part. Okay. Any questions? No. All right. So let's do another exercise then. Let's do exercises 12 and 13. They are actually pretty much the same. Let's start with exercise 12. A single-phase bridge rectifier has a purely resistive load of 5 ohms, a peak supply voltage of 170 volts, and a supply frequency of 60 hertz. Determine the average output voltage of the rectifier if the source inductance is negligible. The transformer inductance is negligible. So what it would be, this question has a lot more information than we need. We have an input of 170 volts. We have an input of 170 volts at 60 hertz and a voltage of a load of 5 ohms. The question is, what is the average voltage V0? Oh, that's simple. If V in is 170 volts. V average is, what is V average? Is 2 pi times V in, and this is around 108 volts. What would be the average current through the load? Is the average voltage divided by the impedance, which is 5. And that, did I calculate that? I didn't, but that would be the average current through the load. Nothing really extraordinary here, very simple. You probably wish that these are the sort of questions you get on the midterm. If it is, there's no complications here. Yeah.
So is the 170, is that the peak or the RMS value?
Good question. That's the peak. That's the peak. If this was given in RMS, then we would have to convert that to peak voltage before we do this calculation. Very good question.
So for the V average, we always use the peak value?
Yes, always the peak value.
Right.
Right. If you look at this question here, Vm is 170 volts. Right. So on the sinusoidal waveform, that's the peak part. All right. So we did the first part. That's 12. Let's do 13. In exercise 13 is the same circuit. We have the same circuit. But now we know that the transformer has a leakage inductance of 0.5 millihenry. And let's determine now the average output voltage of the inductor. So the voltage drop across the inductor because of its own inductance. In the example we had, before, we disregarded the inductance here, but now the transformer has an inductance, a leakage inductance. So what is the voltage drop here that will occur? So let's do that. I have my notes. All right.
Question, sir?
Yep.
So since there's a resistor between the transformer, does that mean does it split the value of the inductor, or how does that work when?
No, this is from each side would have the same inductance. Each side, this part or this part would each have 0.5 millihenry.
Oh, okay. All right.
Okay. All right. So if that is the case, then this is our equivalent system. The load, the voltage across this part here, considering that we have a 1-to-1 ratio, and the inductance of the winding itself. So what is the impedance in this circuit? The impedance in the circuit is 5 plus the impedance here. What is the impedance there? The impedance in an inductor is L times omega J, right? Or 2 pi times 60 is the frequency of the input times 0.5 times 10 to the power of -3. And this is 0.188 J ohms. This is the reactance of the inductor at 60 Hertz and given 0.5 millihenry. So our total impedance is 5 plus 0.188 J ohms. What is the current in the system? The current, the average current, is the average voltage divided by Z, right? The magnitude of the impedance. So this is 170 times 0.6366. That's the average voltage. divided by the magnitude of the impedance, that's 5 squared plus 0.188 squared. And this is 21.26 amps. The voltage drop across the inductor, VL, is simply, or the average, of course, because you're dealing with average current, is the average current times X equivalent, right? The reactance of the inductor itself. And this is approximately 4 volts. So there is a voltage drop across the inductor of 4 volts, a average voltage drop. So the voltage across, the average voltage across here will decrease now, not necessarily by 4 because we are talking about the average, but it will decrease compared to the case where this inductance was neglected. The average drop will be 4 volts. Let me ask you this question. If we had a full bridge rectifier, such as this one, what would be the voltage drop here because of the diodes? Each diode has 0.7 volts drop. So we are always passing through 2 diodes at a time, which means that the voltage drop with a full bridge rectifier would be 1.4 volts as opposed to 4 volts that we have there, right? And then the transformer is also gone. So most of the time we are looking at the full bridge rectification than applications with this.
Question, sir?
Yeah.
So for this question, where we use the L, where is this L, like as opposed to the first question? Like, did we ignore an inductor? Like, how different is it from the first question?
Now the first question here, we ignore the inductor. You only had the load. In the second question, the inductor represents the leak magnetic field through these 2 coils there.
Oh, okay. So we did ignore that.
Yeah, each of them has an inductance of 0.5 ohms.
Okay.
Okay. Any other questions? No.
Just a quick question. So in this
Yep.
example, we're pretending it's like an ideal diode and that there is no drop in the top right?
Aha, exactly, because that would need to account for 0.7 volts drop there every time.
Okay, awesome.
Right.
Thank you.
Yeah, good question. Yeah, because now I compared this with the other full bridge. So yeah, we would need to account for 0.7 drops there, volts there.
So then would be 3.3 voltage drop, or
That would be, it would be, this is only across the inductor, right? The average across the inductor. Then the average across the diode, each diode would be a additional 0.7.
okay. All right.
Okay, any more questions?
Professor?
Yep.
So that equivalent circuit you have drawn there, that's basically like the, let's say one of the cycles of the
Yes,
of the
one
other
cycle.
circuit, right?
Yeah,
Okay.
one cycle.
Okay.